It's my great honor to introduce Professor Abani Patra from Tufts University. Professor Patra is internationally recognized researcher in computational modeling, data-driven simulation, and uncertainty quantification. So please join me in welcoming Professor Abani Patra.
Honor and pleasure to come here and talk to you. It is difficult to speak. Anyway, so it is interesting to go after the NVIDIA talk because my talk will be kind of orthogonal to that. We'll talk a lot about things that don't work. That was all about all the things that work. So hopefully we'll learn how to make things work from things that don't work. We'll give it a minute more. But the question that I want you all to start thinking about, what's this AI business doing to science? Because science has been around for, several hundred years, depending on how you define. So what's big deal about this? Why is this new? Because AI itself is also not that new. Anyway, to continue my thinking, if you think about the fundamentals of how we've been modeling things, has that changed? And if so, how? The point I want to make to you is talk to you today from long way off, Tufts University. And I'll tell you one thing already, you all are about 10 times more patient than my students. By now my dean would have heard about it. His classes don't start on time. Anyway, so I want you to take a minute here to start thinking about thinking, okay? Because the whole point of AI, I think, is to change how you think about problems, how you think about predictions in general. But this is not new. There's a gentleman by the name of Vannevar Bush. Some of you may have heard of him. He happens to be an alumni of my college. That's why I have to be proud of him. But he wrote this in 1945. Automation of reasoning and thinking. 1945, it's still online, you can find the article. He was also the founder of many initiatives in the US, including the NSF. But this is the point that he made, that if you manage data and information, you manage human inquiry. If you manage human inquiry, you manage thinking. He actually thought about creating his own little device in his technology using microfiche and robots and so on to have information accessed to you automatically, immediately. And that's what we are doing now. What does it allow you to do? For about 30, 40 years now, those of you who have done computational modeling, that's been the strategy. There was some observation, whether it's I think you had some 6 or 7 wonderful examples in the video before. There was some analysis, created a model. Could be Newton's law of motion, could be something a little more fancy, fusion model, this, that, energy. But there were a few governing equations and laws and so forth, and we applied them. We made up parameters where we didn't know them, hopefully informed by some knowledge of information. You're predicting weather, you're predicting climate, you make up more. The harder the problem, the more you seem to make up. But about 10 years ago, 2010-ish, maybe a little bit, this nice, wonderful linear cycle we had started getting a little mucked up. This modeling thing started getting into the middle of the data process itself. Okay? What we were doing with data was passive before. Now the data itself and the model itself are both in some sense interchangeable. You start thinking of model algebras, you start thinking of data as a model, and data itself is not always a necessary simple thing that we just observed. Very often in this more complicated, you saw that fusion thing. You can't observe what's happening inside a reactor. you infer it from some other third observation, another model. And every time you do a model is a cartoon, a representation of reality. So you will immediately think about two things: error, uncertainty. Because you're uncertain about the observation, the instrument might have messed up, the relationship between the observable and the thing you're interested in might have changed, all of that. So this was about 2017. I was in the Department of Energy in those days. So we're thinking about two things. One is this AI thing is coming. Second thing is Google is spending $1 billion a year, and I got a $20 million budget. So what is it that you can do that is crucial and complementary to what's going on at scale? That's kind of where this talk will be, and SciML actually needs it a lot. One of the things that came out of this report actually is the term SciML. And there was some controversy about that. My wonderful colleague Steve Lee wanted to call it SciML. I said, what, as opposed to unscientific? Other machine learning is unscientific. But there was a certain logic. We had SciDAC and he made SciML, and it's stuck. And 9 years later, I'm giving a lecture on it. Steve will get a kick out of it when I tell him that. Anyway, so the world is, I'm going to switch now, because all this thinking and why do we need to think better? We need to think better because the world is full of wicked and hard problems that we have to solve. Okay? If you're not working on a wicked and hard problem and you're under 40, change your life. Go find something wicked and hard to solve. If you're over 60, maybe you can relax. But that's where the fun is. That's where the latest technology should be. And that's where humanity will be improved if you solve one of them. I'll show you a few. I've been uniquely blessed to have had the opportunity to work on these. The first wicked and hard problem I started working is of both human interest and is just a fun problem. We're looking at volcanoes. And this was 20 years back. I started working on them. I came to give a talk somewhere, and everybody looked at me. There's no volcanoes in India. Why are you talking about this to us? Well, a couple of things. One is, a computational scientist, that's such a beautiful problem. It's got every scale possible, every physics possible, and so forth. Second thing is, now you do have volcanoes in India. You see the bottom there? That's the Ethiopian volcano that stopped flights over Delhi about a month ago, give or take November 24th. So you do need to care about that. And unfortunately, because of the way that technology is, you'll see the forecast that was given to you. Even for weather forecast, it's much worse than even weather forecasts. The ash forecast is much harder. On the left is a problem I worked on where you do this landslides and so on, where you have some complicated, messy things going on. Here's another one. We worked on this, 2013. This was about a Bhutanese glacier lake outburst flow. You've had more recent ones, Uttarakhand and so on. So these are becoming problems that are important. Looks like I was a little bit ahead of my time. Should have waited. Anyway, so the traditional way we had it, Aristotle to space shuttle asset, this is how that was done. Shish Kumar and I, we all had this wonderful idea that we'll learn how to solve these PDEs because that seems to capture all the knowledge in the world, right? Newton's law of motion, Navier-Stokes, energy equation, Euler equation, you do it, you're done. And they were hard. They were hard. They were not easy. Don't think that we were lazy or anything. It took a lot of effort, but we worked out ways to solve this. There were things like adaptive mesh, parallel computing, supercomputing, all those things came out of that. However, there's still much to be done. We produce these tools, they're out there now, and everybody can use them. The key notion of prediction is still poorly understood. You give me a problem, I can solve it. I can approximate it. Okay, but what about prediction? And even these things we solve are ultimately some kind of approximation, right? How good is that approximation? I want to talk about this landslide here. How much water was there? How much mass came down? How do I deal with that uncertainty? And again, what happened yesterday, modeling that is nice, gets me a bunch of papers, doesn't save a single life. Right? So how do I jump from the past to the future? Some more fun here. Okay. Simulations are complex and great, but what about forecast? Okay. I'm not saying that these are not necessary. These are necessary for a variety of reasons, as you will see, but these are not adequate. This notion of just building models, complicated models, solving them, that was nice, but that's not enough. Here's another problem. So this is a hybrid rocket. What are hybrid rockets? These are rockets made with simple fuels like paraffin. Okay, so you don't have to blow them up. Every third rocket shouldn't have to blow up. And paraffin does have the caloric quality needed. Unfortunately, it doesn't combust in a stable way. So can we learn how to do that? So we had a nice long project for the last 5 years. We just about finished it. NASA has been trying this for a while, but it is hard. It is hard, and one of the first things we discovered was we don't even know what the chemistry of paraffin burning is. I mean, 2 million years of candles, you think they'd know that by now? But yeah, after carbon-8, that's hard to know. So getting back to my debris problem, how do I talk about the future? So here's a simple strategy. We were very focused on this post-fire debris flows. You know how when the fire goes, after the fire, the landscape is much more amenable to landslides because the trees are gone. And the other thing that happens is that even the soil, because of the fire, it's like a ceramic. The water just comes right down that. How do you predict that? So that's what we've been focused on for a big project last few years. The question is this. Again, prediction is the game. So the only way I can predict is if I look at all possible scenarios, I look at the uncertainties associated with that, and the favorite tool of prediction is probability. Okay. If I can give you a probability that your house will be hit by a landslide tomorrow, you're going to run out of there. But with what confidence can I do that? The probability is 0.2. You'll go out of there. Probability is 10 to the minus 6. Yeah, I don't know. So that's where things start getting interesting. There are fundamental issues with this probability model itself. That probability 10 to the minus 6 of what? What is the event space? But those are things that we will debate forever. But the idea that you can provide a quantitative estimate, that's useful. And the way we do that is if we know all these complicated simulations, run all possible scenarios. You take your favorite distributions, you sample, you take your million simulations, and you do it, right? And then you have a probability. You do a Monte Carlo type simulation. You can estimate, you can give me a terrain, I'll tell you this is the probability that this area will be hit by this. You can make it conditional to a large rainstorm, conditional to a series of large rainstorms, or you can also try to bring that in also. What is the probability of weather happening? It's just like you do precipitation forecast, maybe you can do a landslide forecast, right? So that's machinery we've done. It's easy to do, I think, in some sense, because the hard part was the complicated simulation. Then it's just a question of lots of simulations. Each simulation takes 10, 15 days on a supercomputer and so on. Of course, the problem has to be worth it. Who's going to pay for it? Some problems, they'll pay for you. You want to predict a nuclear reactor blowing up, maybe somebody will pay for it. And the gentleman that came before me talking about some of those wonderful defense things, maybe they'll pay for it. Landslides, not so much. It's not that much money. So we end up doing a little bit more. We end up creating these surrogates. So what's a surrogate? By its definition, it's not a real model, right? Actually, that's not true. It's just another model. It's just a model that's cheaper, faster, and if you do it right, actually better. Because remember, these simulations are coming from a particularly rigid framework. Partial differential equation, approximation, solution. If I talk about that landslide, one of the interesting processes I was talking about with faculty earlier, the entrainment process. Okay, soil, boulders, trees, everything is picked up. Do we know how to model that? Are we ever going to know how to model that? But the PDE solver will only solve that. So I have to figure out how to build something that captures all that uncertainty. Okay, and that's the kind of thing one does with this ensemble methods, and I'm hoping that with these AI methods, the ability to create and learn relationships between complicated data sets on the fly dynamically. So I don't have to know if the model is sigma equals e to the epsilon to the power 2.3 plus gamma to the something something. I have an input-output model that works for this range. Okay? So that is much easier to do. And that's where the surrogates come. So a general strategy, you characterize your data and model uncertainty. There's two uncertainties, data and model both. Okay, the model itself can be many forms, so we have to learn that. You use ensembles, and then you represent everything with this AI, machine learning, more classical machine learning Gaussian processes, and I'll show you that sometimes the classical is important and probably necessary. And then you generate all these probabilities by some kind of Monte Carlo process, okay? And then it works well. Otherwise, I wouldn't show it to you, right? So I can get these probabilities. Now, how you believe those probabilities, how do you validate them, those are still somewhat open questions, because validation means I need events. How many volcanoes will I have? How many hurricanes of magnitude 5 will I have? And so forth. So there are some issues with that, but bottom line is. So this is another example. This is that hybrid rocket business. That's a whole ensemble of things. But what is interesting here, you look at that box on the thing here in the corner here. Is there a pointer here? Yeah. Look at this guy here. So one of the things that's very hard to tell is when is a particular point in flame and not out in flame, okay, inside any combustion simulation. There are all kinds of interesting heuristic relationship phenomenological models for that. So that's very hard to do. So what we have tried to do, and this is still work in progress because it sometimes works, to create a separate neural network model that only captures this transition to flame. And that can be trained not with this complicated hybrid rocket simulation, that can be trained with simple 1D calculations of a flame. You see the beauty here. Just like Hooke learned sigma equals E epsilon for elasticity, we can do this using neural network type models for much more complicated things. And there is a lot of power in this inside the loop as opposed to outside the loop. So I talked about many scenarios. Now you're talking about inside, just understanding the model itself. Okay, so that's kind of another interesting summary of the whole thing here, that now we have our complicated computational model. We have a surrogate which allows us to do this thing very fast, and if it's done very fast, one can do both many scenarios, and one can also do an inverse problem. That is, given observations, I know where the landslide ended up, I know what the end of the flame was, the video I have. Can I guess what the input parameter, what was that input model, what was the characterization of the paraffin burning or the entrainment? Okay, so that can be done. But the key was the surrogate technology. Now this is, remember that first slide I said that the data and model are getting all messed up? Look at this. So this is just a simple piece of wax burning, okay? It's about yay big, nothing particularly fancy, very fast cameras. Now the problem is when you start burning this thing, all you get is splatter. And from that, you have to detect what is the surface and how fast is this regression rate. How do we do that? Those photographs we got, that goes through this big UNet model, okay, which has its own uncertainty. And out of that comes some PDF of that regression rate, okay? Some probability distribution function of that. And then you can inform that, and that goes this thing. This is the camera. My wonderful postdoc spent 6 months understanding everything that the camera was doing, trying to understand the uncertainty associated with the different angles, different lighting, this, that. And at the end of the day, we get a nice characterization of that regression rate. So to summarize, there are classical methods many of you are familiar with, Gaussian process regressions. Anybody remember that stuff? I'm sure you do. The problem with that is it works well, but it doesn't do certain things well. Remember, we are burning this piece of wax, so we get some very interesting, narrow, local, multi-scale events. That physics is poorly captured by this. And unfortunately, this was even worse than this, so I don't even want to show those results. But, so we cooked up something very specific. The nice thing about classical machine learning is it's very open and very transparent. You can control it exactly. So we created this new hierarchical multi-scale surrogate, and that was done just looking at creating basis functions of different support. Okay, small ones, big ones, I'll show you in a second. Look at that. You take 20 of these, okay, and then you create your own surrogate as a complicated combination of these things customized to the data. Training time is annoying, and two things happen. One, I can prove some wonderful theory. This is robust, reliable, and I can prove that this is going to give you this thing. For any mathematicians in the audience, you have to have at least one theorem. I have a math department affiliation. Here's my theorem, so I'm off the hook now. But this is a useful theorem. Because when you do the neural network, you don't know what you modeled. You don't know if that's converged to the true underlying process, because all you have is some samples of data. Is that good enough? We'll talk about more of that in a second, but this theorem tells me that, yes, it is good, and it's going to work. And I had a very bright Indian student who did most of the work on this, Prashant. So now you see, so this is where the trouble was, because there was a huge spike there because of the way the wax burned, and the GP didn't work so well. The neural network essentially gave up the ghost. And this is simple. This is not big data, little data, okay? Tens, hundreds. So let's not worry about the data here. Just the ability to represent some of this is hard. This multi-scale does it beautifully, okay? How many scales are needed? What kind of convergence do you get? What kind of compression you get? All of that. You can read the paper. It's a lot of detail. The paper just came out in Propulsion. Now going back to my debris problem, you're all going to get huge back and forth with my problem switching, but I think I want to emphasize that these ideas are universal. They work for very complicated problems. So now we have actually got a neural network that works here. UNet, skip connection, and a few more tricks. Because when you're trying to do full flow field calculations, the standard approach is where you tile it so that you augment the data and get a lot of data out of it. That's a little problematic. So we did some little tricks, for example, using a whole simulation along with tiling simultaneously. That improved a lot. A few multi-scale resolutions, that helped a lot. So a lot of engineering tricks had to be done. But then this works quite well, and our process works. Okay, so the paper's in review, but there's an archive version if anybody wants to look at it. Okay, but life is always more interesting. I know everything about one little bit of wax. I know everything about one mountain. Unfortunately, the next landslide is in a different mountain, for which I have 3 hours notice that hurricane of X, cyclone of Y is coming. What do I do? So the questions of modeling and prediction, how do we do all this? So how to extrapolate? I think this question came up yesterday also in the SciDex session, a little bit. And I was smiling when I said, okay, so she's already explained it, I don't have to explain it again. Models are predictive, When a model is predictive? If the training data is representative, then the models are predictive. Very simple. Interpolation is great. Extrapolation, you need a model that's powerful. Navier-Stokes, for all its fault, the PDE models, Newton's law of motion, they are extrapolative. Okay? Neural network, not so much unless you do it carefully. Okay? So that same power of, so this is what I was trying to say, that you have to know when can you extrapolate. Okay? Now the standard answer is, well, I'm the model user, I will know. I know what I trained it with. Well, you borrowed John's foundation model. Do you know what he trained it with? Not a chance. Not a chance. So with these data-driven models, this becomes a very important consideration. So let me show you an example here that we trained on 3 mountains. How do I go to mountain 4? I do not know how to solve this problem in the general, but I'll tell you a specific example where I think we've made some progress. Okay? So what is the idea? The idea is the following. Is the new site prediction model prediction in the prediction range? So let's think of a standard model that's a function of some training data and some training algorithm, right? Then you have a prediction that is a function of some prediction scenario and your model. So that's the chain, right? That's what you've been doing. So my hypothesis, if the distance, however well measured, and this is going to be a tricky part, how do you define distance in these training data sets, between your prediction scenario and your training data set is smaller than some tolerance, then the prediction is likely valid. And all of that will depend on your distance measure, your tolerance, and so forth. So if you have a particular application, you can probably cook up all these things. So in this case, I can give you specifics. The training data is rainfall, basal conditions, flow rheology, computation process, and most importantly, the topography. Because I said I've trained on 3 mountains. The thing that really changed is the topography. The other things are invariant. So can I look at the distance between the topographies? Because that'll do it. So simple measures, Euclidean, not working. Of course, this is Earth, right? So Earth mover distance just stuck in my head. Okay, that's got to work. And of course, the Sinkhorn process allows you to approximate the Earth mover distance. For those of you not familiar, the Earth mover distance is just simply you have a pile of sand, you want to transform it to another pile of sand. What's the cost of doing that? That's the distance. Okay, so the more dissimilar they are, the more the cost. So optimal transport people, anyone here, I'm sorry for that simple explanation, but it does capture the sense of what I want to say. It is an optimal distance, optimal transport distance. So we did this. But we did another little trick here, because you think about one mountain that has 1,000,000 points, another mountain 1,000,000 points. The Earth mover distance between them is computationally 10 to the 6 to the 10 to the 6 again. Not going to happen. But we can do something very easy. We can do a dimension reduction. So we ended up clustering the topography into 5 bins. Just 5, slope and curvature and so on. Just 5 bins. And these 5 bins now, mountain 1, mountain 2, mountain 3, you can see that they're very different. Okay. Now these 2 are somewhat similar. This one's a little bit more. But this other mountain, which is at the new site, very different. Okay. And this is very computable because between 5 and 5, the clustering does take a little time. Spectral clustering of a topography down to these bins will take a little bit of time. But then after that, the Earth mover distance is trivial. Okay? So that's the Sinkhorn process. Okay? So once you have done this, and of course, now they flow actually all the predictions that we made between the mountains that were similar, where the bins had similar signature, work fine. Because my prediction is in the training range. The distance of the prediction scenario from the training scenario is below my threshold. There's a lot of learning to be done on what are good thresholds and so on, but I think the basic idea of taking your prediction scenario, and making sure it is close enough to your trainings is necessary. And it has to be part of any model's total process. So there you go. So after that, once you've done that, then with a little bit, even the one that didn't work, you needed to do extra training. And after you did extra training, 6 more thing, you can see that the distances are coming down and it's going to work. So there you go. So that absolute error starts going down, okay, with the retraining. But you don't need, the initial models were built with 512 simulations, each of them 8 to 10 hours. I just need 3 more, 6 more simulations at most. So a tremendous cost saving in extrapolating to a new based on everything I've done before. Okay. In a way, it's a crude version of a function model, I'm told, but okay. Okay, how much time do I have? 2 minutes? Done? Done? 2 minutes, okay. So this is a Fourier neural operator. I'm not going to go there too much. All I'm going to tell you is that you all know that FNOs are frequency limited in some sense. They have a lower frequency bias, right? That we are starting to work on some of these offshore wind turbines. For that, that's a bit of a problem. So we built these FNO models, but what we did before we did that, that's the FNO error. Hopefully Mishra will talk about this, so I don't have to go into it. Last talk on Thursday, I think he might hopefully go there. We created a nice little test case. 2 masses, 2 springs, right? We did that in high school maybe. But we cooked up the springs to reflect some complicated, realistic scenarios of interest to us. And we wanted to see if the FNO would work, okay? These are some measures, energy ratio, because 2 things about this. You want to make sure that you're preserving energy. You want to make sure that this spectrum is preserved, okay? So 2 error metrics. And you can see that for the linear cases, things are good. For the nonlinear cases, it's just the two masses and spring. It does not work, okay? So for linearity and so on, so because FNOs act in this fashion, frequency selective filters, the failure is architectural, not statistical, so just throwing more data, because I showed you, those 2 springs and masses, I can get all the data I want. And as a function of data size, we have all kinds of data. But getting back to this one here, so can we fix? So this is the classical representation of a Fourier network operator. So you look here, buried in here are these weights, okay, before you do the inverse Fourier transform. That's, if you can play with that somehow, even if I can probably improve that. And that's what we showed in this paper that just is out on arXiv, that we do a spectrogram loss. So in addition to your MSE, we add the spectral loss. The spectral loss is related to the short-time Fourier transform. Okay, you take windows, you do the short-time Fourier transforms. So this loss goes after that thing I just showed you, that weight in there, and that actually helps a lot. That helps a lot. It's not perfect, but now it's much better. Okay. So linear is good, nonlinear is not good. Unfortunately, when you start doing these things, linear is good most of the time, except when you start looking at disruptions, sudden stop, blade failure. Then you start exciting all of that. So neural operators are good most of the time, except when they need to be good. So that's pretty much all I got to say about them. Thank you very much. I will take any questions that the boss will allow us to have.
We will take one quick question.
Yeah, sir, thank you for the talk. As from a geoscience student, I really appreciate the works on the landslide and the volcanoes. So I just want to ask, like, in your study or in your research, do you also do like modeling of the earthquake or the forecasting of the earthquake?
No, stayed away from that one. No, I've not done any work on earthquakes. I have many friends and colleagues who do that in civil engineering in the structure side or in the geoscience. But no, My hand's full here. Okay.
Thank you. Any questions, please use the live session right there for the questions and discussion.
Thank you so much.
Just a small comment.
Well, my apologies for keeping you from lunch. Hopefully the lunch is good enough that you'll forget.